So the tangent graph, some of you already know how the tangent graph looks like, but I just want to explain why it does the weird thing it does. So for example, we've got our unit circle here. And remember the tan is something over something. What's something over something? It's a sign on cos. And the same way of saying that, it's the y coordinate over the x coordinate. So let's just explore it over here. At angle 0, we want to do the y over the x. So if I just put that like so, what's my answer? 0. It's a 0. So at 0, it's 0. At 0, it's 0. Let's move over to this angle here, pi on 2. I've got to mark this pi on 2 now. Let's do that again. If that's my x and my y, I'm going to do my y on top and my 0 on the bottom. What's a 1 divided by 0? It's undefined. Okay. What does undefined look like on a graph? It's not there. The lines will avoid that space as much as possible. So therefore, if it's not there, we create a space where the equation is going to avoid. And what do we call that? An asymptote. Okay, which is over here. So we have an asymptote at pi on 2. Okay, let's go this way. Negative pi on 2. That's positive pi on 2. This is negative pi on 2. Once again, you get your y coordinate over your x coordinate. Once again, undefined. So if I'm going left, we have another boundary, another asymptote, like so. Everyone's still good? Okay, so what happens in between in here? So if I'm going from 0 to pi on 2, I'm going from 0 to pi on 2, we have this curve going around here. Okay, and what that looks like, what if you do it on your graph, it's going to look like this. Okay, if I go this way to negative pi on 2 or 3 pi on 2, it's going to start curving this way. Now let's think about it. Let's try and get some random variables of why this is doing this. Let's get a dot right at the end. For example, can someone estimate what the x coordinate for this dot here would be? What's the x?
1.
It's not 1. 1's over here though.
0.1.
Oh, 0.1. Well, let's be real. Let's just exaggerate. Okay. And what's the y coordinate of this dot here?
0.9.
0.9. Let's exaggerate. It's almost there. Okay. Now, if you put this really, really big number divided by a really, really, really small number, really big over really, really small, are you going to get a big number or a small number when you divide them? Good, big. Because you've got something really, really big and you're dividing it by small pieces, but there's so many of them. So many of these are fitting in here. It's a big number. That's why it shoots up when it's approaching 1. Are we good so far? In the same way, that when we go the other way, you'll get a really, really big negative number down here. That's why it shoots down. Let's go to the other extreme. What's a good coordinate for this guy here? What's a good x coordinate? Zach, what would you estimate the x coordinate be? 0.9999. Okay. And our y coordinate's pretty small, so they kind of swap. But when you divide them, if you do a tan over, you've got a really, really small divided by really, really, really big. What value are you going to get? Are you going to get a really big answer or a really small answer? Really small. So that's why at angle zero, it's already zero, but around it's really small. So that's that there, and that's that there. In the same way, it works in the negative direction as well. That's why you got this weird thing happening. And so as we keep going round in a circle, we keep repeating this pattern all the way through. Because these values, you're just spinning your wheels. You're still getting these numbers, really bigs and really smalls every single time. So if I've done one, I can do all of them, and you can go on forever. But if I've done this one, I can now sketch that. If that's pi on 2, what's this? No, this is pi. Good. All right. And we've got our intercepts over here that are being repeated all the way through, like so. Any questions? Correct. It's my bad. That's pi. What's this one here? 3 pi. Thanks for that correction. Okay. All right. So that's where it's coming from. Let's do one or two examples. Over on the right, which is something you need to be familiar with every single time, is the general equation for tangents. A stands for, what does A stand for again? Dilation. Yes, a bit more specific though for trigonometry. It is a dilation though, yes. What's the word though? Okay, amplitude. Okay. And notice the difference for our period. It's pi on n. What is it for sine and cosine? 2 pi. 2 pi on n. It's different for the tangent. Has anyone seen this before? Okay. I'm just going to do a few examples. Notice that asymptotes here, they just repeat all the way through. But you'll see something happening with 2k plus 1. If I have a 2k plus 1 in my equation, what is it really doing? K is an element of z or z. What does z mean? It's the natural counting numbers. So let's do the first one. If I naturally count, I'm doing 1. So 2 times 1 plus 1 is a 2 plus 1 equals a 3. Okay? So k equals 3. If I do k equals 2, what am I going to get? 2 times 2 plus 1, so 4 plus 1 equals 5. Even if I do k equals 0, 2 times 0 plus 1 equals 1. Notice our ending numbers. 1, 3, 5. What does that mean? With our asymptotes, I can get the first asymptote at 1. That's now 1. So 1 pi on 2n. Okay, I'm just ignore the n for now. I'm going to go at 3 pi on 2. N is the next asymptote. And it keeps jumping every single time. If you look carefully on our original graph, our first asymptote is at a pi on 2, which is a pi on 2. Our next asymptote is at 3 pi on 2. So this counting function helps us to identify where you put your dashed lines. The reason why the n is there, and what do we know about n in sine and cosine? What does it do with the n in front of the x or the t? What does the n influence? It's not the shift. It's the period. How many cycles? So when there's an n on the bottom, it helps you calculate that as well when it's different. Here, this intercepts is the really easy counting. So pi on n, it could be 0 pi on n, which is 0. It could be pi, 3 pi, and so on, the asymptotes. Okay, so pi here, first intercept, okay, which is this one here. And then so on, depending on, and you can even just do the first one and just count, but this one will help you do it mathematically. Okay, let's just do one question so you can get some work under your belt today. Just wipe this off. Okay. Let's just do that for now. Y equals 2 tan 4x between negative pi and pi. Now, best thing to do is a 3-step process every single time. You've got your period, asymptotes, and intercepts, and that should be enough information to do repeats all the way through. So if I have pi and n, how wide is my cycle for this one here? 4. So pi's on 4. So in your head, think quarters. Okay. All right. Let's go over here. What can we now change in our counting for our asymptotes? The n. 2 times 4. So 2k plus 1 pi on 8. So just to simplify things in your head, this is counting. That's just simple count. But we're counting eighths all the way through. So quarters and eighths are your main markers along the route. Here, k pi, once again, just whack in the end. 4. Our intercepts are happening at quarters. Okay, so what does that look like over here? So there's no shifts or anything, so we know it's going to just anchor on the 0. But as I said, we're looking at quarters and eighths. What's smaller, the eighth or the quarter? The eighth. So that our first dash, our first one is a pi on 8. Okay. If I do the next one, that's going to be a quarter. And then it'd be a good idea to just keep going. Okay. Pi on 8, pi on 4, but I'm at number 3 of these ones. So therefore, in my mind, what's the fraction if this is 3 times bigger than this first step here? A 3 pi on 8. Okay. Over here, pi on 2. It's a pi on 2. Good, excellent. So the pi on 2, but if you're in eighth world, you can have that 4 pi on 8. But it's better just to simplify it. Okay. So have a look. Asymptotes are at our eighths all the way through. So I'm just going to go pi on 8. That's my asymptote. That's my first one. Okay. Where's my next asymptote? 3 pi on 8. Remember, these are counting practically in odd numbers. Okay. And we can go backwards here. It's better to do the central one first, which you can replicate all the way through when you need it. Okay. So therefore, nothing special too much about this. It's a positive 10x. There's no negatives in there. So we do that. Have a bit of fun as if you're painting a picture. Okay. And we can go all the way through. Okay. Tell me what fraction this is.
5 pi on 8.
5 pi on 8. 6 pi on 8. 7 pi on 8. 8 pi on 8.
Just pi.
Which is just pi. This can only be 7 pi on 8. Can't simplify. This can be
3 pi on 4.
3 pi on 4. Correct. Okay, good. Do not use these to help you, but stick with these. Okay. Like so. Once you got asymptotes, just whack in your squiggly tangent lines. Whoops. Okay. Now here, looking at our domain, we want to get up to pi. I'm already at pi. I can't go forward. So when I go back, am I going up or down?
Down.
Going down. Is this a coloured in dot or an open dot?
Open. Closed because it's the end of the domain. Let's try something so.
Okay. It's end of the domain, but do we include the domain Perry, or we open it up?
Yes.
Include it, and included is coloured in or uncoloured?
Coloured in.
It's a coloured in. Okay. Are we finished with this graph?
No.
No. Okay.
We got to go the other way.
Excellent. Okay. So you go the other way.
Yeah, we get
Okay.
the picture.
Get that picture. Okay. You're telling me to stop there, does it say that? Okay. You get the picture? I'm going to leave it there. It does get a few variations, but we're going to spread it till tomorrow in our double period. Any questions?